Hey everybody, this is Larry. This is me going Q4 of the the regular weekly contest 258. Smallest missing genetic value in each subtree. So this one is very hard. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. This one is a very competitive E problem. So if you like these competitive E problem, come talk to us in Discord and just chat about it. And it seems like people actually did better than I thought they would. I started a little bit late though because I had an issue of Q3, and I want to give you a little bit of warning is that my code is contest code, so I probably, if I were to do it again, I would probably change it up. So I'll show you what I have now, and then I'll show you how I would change it up, and then maybe it's a little bit wrong though, but the idea is still the same. So the key one behind this one is that the key observation, which may take you, it took me about 15 minutes to come up with, to be frank, the key observation is that there's only one path that matters. What does that mean, right? That means that, well, given a tree, we are going to bring up paintbrush. Hang on. Let me pull that out. Okay, right, so let's say we have this tree, and let's just use the tree that they give us, but maybe some variation, right? So yeah, and it doesn't matter what they are per se, like the values. We'll draw some lines as well. Right? So the answer is that, okay, or the big observation, which is not an easy one, is that, okay, let's just say this one is a 1. Oops. Wanted to change the colors. Let's just say this one is a 1, right? Well, what does that mean, right? Well, actually, let me change this again. Let's say this one's a 1, just so that it's a little bit more complicated so we can visualize it a little bit better. But let's say this is a 1. What does that mean, right? Well, that means that, okay, that means that the children doesn't matter, in the sense that answer is already 1, right? Does that make sense? These are answered because everything is unique. That means that in these nodes and everything even below them, if they exist, everything below them, the answer is 1 because 1 cannot exist in those cases, right? So yeah, so that's basically the idea here. And so everything underneath is going to have an answer of 1. What else has an answer of 1? Well, this has an answer of 1 because it never interacts, because there's no subtree that includes this, right? So that means that what subtrees can include this 1? Well, you just go up the tree. So this is a 1. You go up. So this we have to calculate, and this we have to calculate all the way up, right? And the reason is because here contains a 1, right? This one contains in a subtree, right? Let's just say T for the subtree. Yeah, subtree. And this one as well, right? So 1 is inside it, right? It's crappy notation. I apologize, but yeah, this is all the 1 because I have to draw with my mouse. So, but yeah, so that means that we only care about all the nodes that are up the tree, right? Okay, that means that all the other nodes we don't care about. For example, here, this one is going to have an answer of 1. This one's going to have an answer of 1, and also all the other, let's just say there are more nodes. They're all 1s as well, right? So these are all 1s, right? Okay. So now we got here, and you can now, if you make that observation, you can notice that there's only one path, right? Because 1 is unique, there's only one path that's the case. So that if we're able to kind of do merging if we're able to do something that's not linear time, then we should be good. Okay. And basically here, our idea is that, okay, let's calculate, and we have to, implementation wise, this is a little bit tricky, but you have to do it. Basically here we calculate what? Well, let's just calculate the set of all the numbers in here and all the children, right? So now we look at all these children and then we get a set. And then here with the set, we just keep on, find the answer for it, which is the answer for this node that we want for our answer. Like in this case, let's just say it's 1. So 1 cannot be the answer because 1 is in the set. It's 2 in the answer. Well, if 2 is in the nodes, then if 2 is in the nodes, then you go to 3. If 3 is in the nodes, so forth. Of course, you maintain this using a set. Okay, so now we get the answer for this one, right? And then now what? Now we go up the tree. So I'm changing colors. I think I used too many colors, but oh well. And then now we go up the tree. Let's say we're here. Okay. This is very confusing to look at. Let's say we're here, right? Well, here, the answer is still just all this stuff. So we keep track. And then we can do a depth first search on the children, right? On the other side that we don't care about. And we only look at each node once. If we look at each node only once, then, well, by definition, it's going to be linear. And then, of course, now you have all these, the left subtree, the right subtree, and I know that there are multiple children, so doesn't have to be a binary tree. I don't think anyway, actually. Didn't see that. Yeah, so it doesn't have to be a binary tree, but now you have all the sets and then you put in the same set, noting that you only care about this depth first search once, right? So you don't have to do some recursive merging, you just have to kind of do it once. So that's the careful thing that you have to care about. And we'll go over the code. But yeah, but here, then now you just go, okay. So you have the previous max. Let's just say here, the answer is 5, right? And this is actually a key part as well. Let's say the answer to this is 5. Here, you start from 5 to go, okay, is there a 6? Oh, sorry, is there a 5? If there's a 5, you go, is there a 6? If there's a 6, is there a 7, ... right? The reason that this thing about it's important that you start from 5 is that if you didn't, and if you go for another for loop again, then you kind of do the n squared thing that we talked about, because then you do 1 again, 2 again, 3 again, 4 again, and then 5 again before hitting 5 again. But because you know that the numbers between 1 to 4 are not possible, you can start at 5, and because of that, you only increment. You only do this incrementation. Is that the word? You only increment one time per node in each subtree, and therefore amortized out, this is going to be linear. So that's basically the idea that I had. Let's get back to code. I will admit that the way that I wrote this code, I don't think is clean code or good code, but I kind of tried to break the problems into different components, and therefore it's a little bit awkward. But if I now know the solution that I have, that we've gone over, if I knew that solution, I would have written this differently, and I can kind of go over where I went. So basically, I break them up separately. Let's see. So this is just parsing the, oops. So here we just parse the children, parse into children so that we can do a depth first search. So that's basically what we have here. Here we have a depth first search. I don't think this is, so you can look at this, and basically the idea is that from the top down, I was trying to find whether the subtree contains a 1. Does subtree contains a 1? And basically, if it contains a 1, then it's no good, and we have to do work later on. But then I later realized that this is not necessary because there's only one, and then you know where it is by you could just do a linear search through the nums array to find out where the 1 is. So this is actually not necessary, but this is my contest code. You can look at it, and then here I processed all the possible, like if the subtree does not contain a 1, I set the answer to 1. So here this is what that does, but we can remove this actually. So I'm going to remove this. For completion's sake, if you're checking at home, take a look at it, but yeah, we don't need it. But yeah, okay. So basically now we have this mock scene thing. So I think that's basically where we can do it, is that ends of current is equal to 1, right? And I'll explain this part in a second. But this should mostly work. If not, then try to program it at home. But the other code that I had was AC, in case you're wondering. But like I said, it's a little bit more, because I broke them out to different parts. So my first part was whether each node has the subtree containing a 1. So that was the question that I asked myself, but you could have combined them. And basically this is where I have, so current is the index of 1. So this is basically going to where the node is. The node in the tree, we go, okay, current, right? And then now for each current, and this is just the set up the previous. We'll go over why the previous in a second. And this is the set of all the numbers that of all the values that we've seen. So we start with 1 because this is obviously the value that we've seen. And then initially we go for the child or the children. And then for each children, we mark it as seen, right? So this is what we talked about, is that we have, we recursively look at each node and then we put it into the scene set, right? And this is basically just a very basic depth first search. You should be familiar with it. If not, there are a lot of depth first search problems to practice. But yeah, but basically we add for each node, we add the numbers to the scene, and then for each number we go, we branch it out. We do a recursive thing on it. And of course we set the answer to 1 because for each of the things that we mark in scene, they are not in the critical path or the important path that we care about, right? So that's why we'll be able to set this to 1. Actually, let me just run this while we talk anyway. So yeah, so this is the case. Why do we not have previous? If you go back to so basically we set previous as the node that we processed last, and basically the idea is that you don't recurse on the tree you just executed, right? Otherwise, that's the tree that you already did the work from. So if you're thinking about going up the tree, let's bring back the pretty thing first. Wouldn't say pretty now that I look at this, but if you look at this thing, which is a mess, basically the idea. Okay, let's just clean this. Okay, that was unintended. Okay, whatever. So yeah, so the idea is that, okay, you have these nodes, right? You have these nodes, and let's just say that, for example, yeah, and then there's way more trees here, so forth, right? And let's say that this is, let's just say that this is the one that we care about. Well, from here, initially we processed all the other ones that are below, right? And then now we go up. Now we're here. What does that mean? Well, we don't want to process this subtree. So that's what, and here we marked it as the previous. Let's just call it nasty handwriting. But let's just call this P for previous. Man, I don't know if you can see these colors are terrible. But yeah, but basically we just do not process this branch. If there was another branch, with subtree, then we process those, right? We do want to process these as seen. So that's basically the idea. And then now once we go up again, we're now here again. We do not process this subtree, so that's basically the idea about keeping track of the previous. Yeah, and then here, so then the idea that we have is that, okay, we also add the current node, of course, and the value, and then this part is the critical part of just adding 1. We do not reset the max back to 1 because otherwise, because we know that as we go up the tree, we already know the numbers that are not possible. And so then we don't have to redo that work. So that's basically the idea. But yeah, it has to be updated because you can add things. But yeah, after you do this thing, you just set the answer to the max. I say max because it's the maximum excluding, which is what this question is asking technically. So yeah. And then at the very end, you just return the answer. So this is, I think this should be roughly it. Let's look at so this matches the answer. So yeah, let's make this, I'm gonna make this slightly smaller so you could kind of see it in one page. But yeah, but that's pretty much it. Like I said, everything is linear time because this is a depth first search, and if we don't look at the same subtree more than once, then each node will get marked once. So this is linear time, and of course this is actually, even though this looks easy, this part also makes sure that it is linear time because we don't redo work. Therefore you only increment this once per node, so this is going to be linear time in total. Obviously it's going to be linear space because of the answer array, but also depth first search has all of h height space, and of course we just actually store O of n because we parse it to a top-down tree anyway with the recursion. So yeah, cool. That's all I have for this one. Let me know what you think. Hit the like button. You could watch me solve it live during the contest next. This works. I mean, this is so, like, I did the same thing but in other directions, so I don't know. Maybe maybe strings are faster and optimized, but it's still very stupid. Okay, only 33 people got this, but unfortunately I have a lot of penalties, so even if I get this now, I have 3 penalties, so that's a little bit sad. Let's see, top people got it in 7 minutes, so maybe it's a problem that I can do in an hour. I should be able to do it in an hour, so let's do that. Okay, there's a family tree. I should so many silliness. Okay. And it's done. Okay, actually read. I was a little bit slow. Okay. Because I'm still tilted from the other one, I think. Okay, there's a family tree rooting at 0, and end nodes from 0 to n minus 1. Okay. You're given the parents, okay, that's fine. Given num sub I, okay. The smallest that's missing from the, so like a max from rooted from I, okay. So let's look at the solutions or the things. So here, the smallest is 5. On the left side it's 1, okay. So basically you're trying to get the max of the subtree. And I assume that if you're sloppy, it's going to be n squared, so that's not going to be fast enough. Okay. I don't know how to do this yet. I'm just setting this up a little bit. But so nums can be any number. Could be any number within range, but it doesn't matter because it's just effectively any number. Because it can be all really big. It doesn't have to be from 1 to I. It's just 1, 2, whatever. Okay. So this is going to be 1, this is going to be 1, and then merges, this is going to be... So the question is, how do you do the merging in a... Oh, they're all distinct. And what does that distinct means? Distinct means that... distinct means that you can't combine them in a, you have to combine them in a smarter way, because if you have a linked list effectively, you can force something that is n squared. So you have to do better than linear combining. Is there a good way to do that? People got this in 7 minutes. Jeez, jeebus. Maybe it's a known thing. Node 3 only has 4. So, okay. Subtree 2 contains 2 and 3, of course. Contains 3 and 4. Still okay. So then I think the combination is interesting. For example, okay, so this 3. Yikes. So this 3 has values 1, 2, and 3, so 4 is the smallest one. Okay. But this is 1, this is, so the answer for the 4 is going to be 2. Two is met, but that's fine. Here, the max is going to be 1. Is there something that we can tell about it properly? Not really. We can construct a sort of a... Can we merge in an effective way? So when you do a recursion, you have to... No, you can't do anything crazy. But you have the max and a list. On the right, you have a mix and a list. If we do prefix sum, it's not good enough. Because you merge in, even worse, because it'll be nlog and merge. Well, if you're not careful. Is there any other sequence that we don't know? It's a tree. Maybe we could think about it backwards. Maybe we can think about it backwards. Okay. You go for the thing and you ask if there's one. If there's no one, and only one of the subtrees can have one in them. So if this has no one, then that means that everything on the right of that subtree is one, right? And then now you go down that list. Is there a one? If there is, so basically for each, and then there you go through the thing. Okay, does that kind of make sense? I have to think it through a little bit more. Okay, so for example, in this subtree, the 4 and the 6 will just have ones. That's fine. And then on the right subtree, we go, okay, we have 1, 2, 3, 5. We want this to be 4, but we do linear time. Well, we go recursively. Okay, 4, there's a 1, so the answer is 2. This, and then 3. Oh, so you merge only in that particular one. But it still can be n squared if you're not careful. So we have to be careful. And we can do it with connected components or something. But now we okay, I think I have a path to solving this, though I don't know if I still know this. So basically, okay, and then you merge the solution from there. But you don't have to do the answer. You don't do the calculation. You only do the calculation on merge. And then it will be incremental because for every time you go up, I'm just thinking whether that's n squared. Oh, let's start hacking some stuff. We should at least able to get a thing. So there's only one path in which the answer is that one. Okay, so let's do that. Okay, let's pause the thing, parents. This is not great. I wish I've gone down earlier though, but this is just children. So is it always the first node? Okay. Okay, no. Does this subtree contain a 1? Okay, let's do that. If and none of the subtree, there should only be 1 1, so none of the subtree will have that either, so okay. Otherwise, okay. So then now for x isn't children of code, go if the first search for x, that means that. Then we return true, otherwise we return false. Good. Then answer of current is equal to 0. Okay. Don't think this is obviously this is not enough, but the ones should match the answer. I was wrong because we have a 5 here, even though 5 contains the 1. It should be -1. Why is this 1? Because we go and then we do it immediately. Okay. Okay. Does that match the answer? Nope. Because it's 7. Oh, I think it's the root again, but why am I having issues with the root? 4 and 2, and then the root. So where's my 1? 1 is 6. Oh no, here's my 1. It's at 4. 4 is 0. So the 6 is 1, that's fine. Why does 5? Oh, 4 and 5. Node 0, 1, 2, 3. Huh? 3, 4, and 5. Oh, okay. No, I'm mixing the numbers again. Okay. So, oh, here's the input. Oh my. So this is on 0, 1, 2, 3, 4. So, okay. But that means that 4, 3, and 0 should be a thing. But why is 0 not good? Oh, I have to return true. Okay. Okay. I think we're good here. Okay, so now we set to write things correctly. Okay, now to figure out what that is. And the only one number increased on this path, right? Okay. Oh, it's a path, huh? Right. I don't even need to do it this way, I think. Okay. I don't even need the children. I just need to do it from the... that's not true, because you need to, for example, in this case, get the 5. It's just that... trying to think how to represent all the subsets of all the other size in a good without degenerating to n squared possibility. So okay, so we know that the wrong answers, or the interesting answers are 0, 3, and 4. How do we merge the 5 in a good way? Or is the 3 in here actually? The node 5, 3. I guess we could share the structure. Okay, I think it's just implementation then. I mean, I'm going to keep this, even though it looks a little bit awkward and I don't think it's necessary. But I want to refactor this, but I don't think it matters that much. So max will have to be 2, and we start at the node in which nums is 1. Okay. I have half an hour, I have to think about it. Okay. Num sub index of 1. One is not in the list. Oh, in this case, okay. If one not in nums, then we just return this. Otherwise, we start here. Okay, let's just go first then. Let's just rewrite this part. This part is so possibly. No, it's fine. It's fine. All right, so now we have okay, I get it. Okay. Scene web 1. And now we go to his parents. But while current is not equal to -1. Okay, we do a depth of search on a thing. As long as we don't go for the previous, it should be fine. When current is equal to the parents, current previous is equal to current. Okay. Okay. Why is this so awkward? add current, and then for child and children of current, mark scene of child. Okay. This should not. I'm just checking to see if we would want an infinite loop. Doesn't seem like it should, so it's okay. It's actually also even print out the current just to be annoying. So this prints 0430. Okay, so that's what I expected. Okay. Okay, and then now we can, after this, go while max is in scene, max to the 1, and also the current, and answer of current is equal to max. Okay, we're close, not quite, but okay, current scene. All right, we start. So in this, is this right? At least the 4111. Nope. That's 1, 2, 3. I'll put 5. Why? Tell me why. Oh, I have to add the current number. So still not quite. What? Oh no, not the current number, the current value. So num sub. Still not right. Okay. The scene part is, well, this should be 1, and then okay, so we've seen the 1, and then that should be good. But then we mark scene. We mark scene 1, 2, and 3 on a 0 node. On a 0 node, which contains 1, we should mark 2, 3, and 4. Why do we mark 1, 2, and 3? Oh, I did the same thing here. Okay, this is giving me the right answer, so I'm happy about that. I'm going to YOLO a little bit. I mean, you probably would test more, but let's just, there's only half an hour left, so if it's right, it's right. If it's wrong, it's wrong. Okay. Yeah, thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Come hang out, talk about these problems and so forth. I did okay. Yeah, I'll talk to you later, and stay good, stay healthy, and to good mental health. Bye-bye.